back for atomic history part 2, where we left off with, we had Dalton's solid spheres, we had Thomson's plum pudding model, and then we had Rutherford's kind of Jimmy Neutron-ish model. And kind of picking up there was an issue with that Jimmy Neutron model, and what it was that why didn't these positive protons and these negative electrons, why didn't they attract each other, and why didn't they crash into each other? Opposites attract, why not? So to account for this, a guy named Niels Bohr comes along, actually with the help of Rutherford, and in 1913 he develops the solar system model. You can kind of think of it like planets orbiting around the sun. Where what he does is, instead of just saying the electrons are out there circling around, he put these electrons in specific paths, which he called orbits. I highlighted here because we're going to talk about something very similar later on. So know that Bohr had orbits. What he said was each orbit has a specific amount of energy, and electrons can gain or lose energy, which moves them either higher up if they're gaining, or further away from the nucleus if they're gaining, or closer if they're losing, closer to the nucleus. This quantized energy, so quantized means it comes in very specific amounts. It comes in discrete, and in this case we think of energy as a packet, just kind of as a whole piece together. This discrete packet where only certain amounts are possible. So what this did is, by saying that there's only certain amounts possible, means that an electron couldn't be anywhere in between. It kind of disappears and reappears right in another ring. So that idea of quantized means it takes a quantum, or again a specific amount of energy, to move orbit to orbit. So I have an example here. Here are orbits, concentric circles moving around. Electrons have to be here, they can't be anywhere in between. And Bohr's model was nice because for hydrogen, so one proton, one electron, he figured out, plus a few other scientists, that an electron, if you excite it and you give it some extra energy, it doesn't like that, so it wants to get rid of it. And one kind of proof for this model is, in this case, if we excited an electron up to the third orbit, that if that electron were to fall down to the second orbit, it has to get rid of that. So to fall down, it has to get rid of this extra energy. And in this case, that specific amount of energy, that quantum of energy, comes out as actually red light. We see it as red light. Whereas he does math for others where I think it's 5 to 2. So you excite one way out to here, actually further out to here, to 5, and back to 2. I think that comes out as a purple light, if I remember correctly. And he did this, well, as many others did this, for all the different kind of progressions you could make. And some of this we can see, others we can't. It just so happens this case, that specific amount is red light, which is pretty cool. We'll see this in class. This worked great for hydrogen, which had only one electron, so it was pretty easy to follow that electron around. But for anything bigger, even for helium, this broke down. So again, science needed this other model, and in comes along Schrödinger. So him, as well as many others, in the 1920s, they developed wave equations, where instead of viewing this energy, these electrons, as packets, we view them as waves instead. And these equations determine where we're probably, which I spelled that wrong, where we are probably going to find an electron. And when you do, you map out where these regions of probability are, they come out to what he called orbitals. So different from Bohr's orbits, Schrodinger has orbitals. And these orbitals are actually three-dimensional. So instead of being flat two-dimensional circles, these are three-dimensional where this is where an electron is going to spend 90% of its time. So unlike Bohr, he doesn't say where the electron actually is. He just says it's in this area around the nucleus 90% of the time. We call this the quantum mechanical model, and this is actually the model we still believe today, where we have these different energy levels, kind of like Bohr, but these energy levels contain one or more sublevels called orbitals. Don't worry a whole lot about the wording here. I'll show you what I mean here in a second and what you're going to need to know. But these sublevels, there are four types of orbitals, if you want to think of them that way. SP, D, and F. And each orbital can hold up to 2 electrons. The first type of shape is just the s orbital. This is the simplest. It's a sphere. And again, this guy can hold 2 electrons. Again, it's simple. It's the first type. And if you don't like my picture, here's another one with the sphere in it and the axes drawn. The next type is p orbitals, and there's 3 types. So in a p orbital, you could have a pz, a py, and a px. You don't have to remember it that way. Just know what they look like. So we know this is a sphere. These kind of look like dumbbells or Q-tips, however you want to think of them. And there's only 2 blobs, if you want to think of it that way. And each of these, so like this one can hold 2 electrons. And this is the space where that electron spends 90% of the time. This one holds 2 electrons, and this one holds 2 electrons. So a total, we can fit 6 electrons in a p orbital. P orbitals, if you don't like my drawings, there's the shape as well. So kind of 2 blobs on each axis. The d orbitals, it starts getting a little more complex. And this all comes from mathematical equations and mapping where that electron should be. But you almost get like 4 blobs for each of these. And then you get this kind of weird thing over here, which is like 2 blobs and a donut. But if we look, this one holds 2 electrons, this one holds 2 electrons, this one holds 2 electrons, and so on. So what we get is, of these 5 types of d orbitals, we can fit 10 electrons. The last one, well, I guess I'll show you the picture of what they might actually look like if you didn't draw like a 6-year-old. Look like this. So you can see each of those 4 blobs, and then you have this one that's 2 blobs and a donut. The last one, the f orbitals, you don't need to know what these look like. You can see how it gets more and more complex as we go through. The f orbitals are just complete craziness. What you need to know though is that there's 6. So if there are 6 different orbitals or suborbitals like you see here, that the f can hold up to 12 electrons. And that's kind of how we view the atom today. Nucleus in the middle here, with these kind of areas around it. If I was a good teacher, I would have had a picture of kind of all of these put together. As you can imagine, it's a huge mess of a whole bunch of different shapes. But this is how we view the atom and where we view those electrons to be. We're going to see the Bohr model so much more because it's so much easier, and it's so much easier to describe where those electrons are, but that is not how we view the atom. So this is the most up-to-date current view of the atom and where those electrons are located.